Good morning. Today we are going to set up the test for hammer excitation or ping test, both in hardware and software. Then we are going to perform the test and see the results. Now first we need to locate the accelerometers. Remember that for hammer test, the hammer moves around the structure and you only need one response point. So one response reading from an accelerometer. I like to put them in the places where they expect to be high responses. So not in the root, but maybe at the tips. So you can use the beeswax that comes with the accelerometer and just push it in. Secure the wire. And this one we are plugging into channel number 5. You will see later why this is the case. Make sure that it's attached firmly to the structure. The hammer, there's nothing really to do here, but just attach the wire, and a hammer in our setup will go to channel 6. Sorry, channel 8. This is it, we are ready to test. Next thing that we want to do is to configure our software for the hammer test. We go in any setup configuration, we go from top to bottom. We'll start with this. We are doing an impact test, and let's change the name for something other than the default name. The timestamp here option, this option is important, and make sure that this is checked in. This will help you with multiple data sets of your tests. Each one will be timestamped and not overwritten over the old one. So make sure this happens. Let's go next. Metadata is not important at this stage. The transducers tab, this is important. So for any transducer, we have 3 options. It can be inactive, which means that it is totally excluded from the test. It can be a response. Your accelerometers are recording the response of the excitation. And the transducer can be an excitation, which means it can be either hammer or a shaker. In our case, we have a response accelerometer connected to channel 5. And we have excitation, our hammer, connected to channel 8. Let's uncheck the default channels. And both of these sensors are ICP sensors. Our accelerometer is around 100 millivolt per G. And our hammer is applying force, and it is around 22 millivolts per Newton. Now for the name. The name is important because it connects your sensor's locations to the geometry that we defined in the previous step. So the syntax is as follows. First we do the name of the component, then dot, then the number of the node. In our case, it is in the 5th node, and dot, and also the direction at which this sensor is measuring. In our case, our accelerometer is vertically oriented. For the hammer test, the name for the hammer is not very important, so we'll leave it as channel 8. Go next. We'll deal with this later. Now the bandwidth and the sample rate. These 2 fields are connected between them. If we change bandwidth, the sample rate will be changed accordingly. You might recognize the ratio is 2.56. This is the Nyquist ratio, and it's hardwired inside, so you cannot change it. So the bandwidth is simply up until what frequency you want to measure in your test. In our case, we will limit ourselves at 400 Hertz. So in any case, in any model test that you do yourself a favor and limit your test at some frequency, because you can measure natural frequencies up until whatever. There will be more and more, but at some point they are just become irrelevant. So our test will be limited by 400 Hertz. The block size, it means that we take the sample rate and we divide it by some number, and this will give us the resolution of our frequency. So in our case, the block size is the same as the sample rate. Let's increase it slightly. So the resolution between measurements will be half Hertz. So this actually can be modified at later stages, but it's a good idea to do your first test with some moderate block size in order for the software not to work too hard. Now, acquisitions per node. In any model case, in any model test, there is no such thing as one excitation and one acquisition per node. So for hammer test, three taps per node is a good number. Because we are recording now, we will limit ourselves to 2 taps per each node. Let's leave it at auto arm and start recording. Triggering. Whenever we exert force with the hammer, the software knows that this is the time to record. So we will leave it as positive slope. Let's reduce the level a little bit. And the pre-trigger of 3% is a good value. So I'm not going very deeply in all the options here, but I encourage you to read the manuals. It includes much more data. Let's go next. We are not doing digital filtering. Now for the measurement. We want the FRF function. FRF stands for frequency response function. We want to record this in order to be able to extract the natural frequencies and modes in the later stage. Windowing. The only available for the hammer test is the force exponential window, and we will stick with the default values. Let's remove the DC offset. Next step. By default, the FRFs and the coherence are chosen. These are good values. So FRF is frequency response function, which is required to do the analysis in the later stage. Coherence is your measurement of the quality of the results. If you want, you can also record the time history of your taps. Let's go next step, and we return to the beginning so we can save and close. We are almost ready to do the test. One last thing that we want to define is our node list. We will, in the hammer test, the excitation is roaming, so we use the hammer to go around the points and excite the structure. We will define the list for the excitation nodes, and we edit the list. So we don't have any X and Y direction measurements. We want to go from node 1 to node 5, and we want to excite them, but we are exciting them in the negative direction. The accelerometer measures up, and we are tapping down. So we are exciting down. And also we have our accelerometer at node 5, which is measuring the response. That's it. We are ready to do the test. Let's change this to 2. Auto arm is okay, and I will see you in several seconds. Okay, now we are ready to begin. We hit play. Waiting for several seconds for the program to initialize. Now the list is displayed here, and the next tapping point is 1. In this window we see the trigger status, and here we see the instantaneous FRF. So we are recording at 5 and wherever we are hitting at this point. Second tap, the same point. See that the data is saved.
TT.1.z completed.
Was changed here.
Please move to TT.2.z.
Notice that FRFs, the shape of them is changing every time we are changing the input location, which is
TT.2.z completed.
Now we are at 3.
Please move to TT.3.z.
3 again.
TT.3.z completed. Please move to TT.4.z.
Z direction, which is vertical. So do yourself a favor and try to do it vertically, not at any angle. So we are at 4. Again.
TT.4.z completed. Please move to TT.5.z.
This is it. The test is finished and we are ready
TT.5.z.
So we have our test. We collected the data. Now we are ready to do the analysis. If you hit here, you will see the whole of your project with all the data sets and whatever you have in each of the data sets. So we have only one now. If you want to explore it to see what you have available, for example, we asked for FRF, for coherence, and for time records. So everything can be viewed. So it's a matter of just dragging. It's there. We can do coherence. So it's drag and drop. To do the analysis, we go to Analysis, and we go to Advanced End-of Operational Model Wizard. Now we have only one data set. When you have more, you can actually choose on which data set you are doing the analysis. We have one geometry. Again, if you have more, you can choose more. And we hit Next. We have 5 nodes, and we are recording only in the Z direction. So XY is missing, which is okay. We hit Next. Let's do this like this. Now you can see the FRF, the function that is presented is usually the drive point. So we are recording 5 and tapping 5. You can also do all of them. Okay. So immediately what you can see here is where the natural frequencies are located. If you remember that natural frequency, natural mode is something that's it's a property of the structure. So no matter where you are tapping, no matter what you are exciting, these frequencies will show in any recording. So you can see that all the 5 FRFs that we have here have peak here, and also we have several peaks here. So in between we have something here and something not very clear in between. Now There are several tools that help you to identify your modes. One of them is the MIF function. So MIF stands for Modal Indicator Function. You can see it here. This function is a mathematical function, mathematical entity, and it will show drops wherever you have your natural frequency. It's supposed to show you, to help you to identify your modes. In our case, we can see 3 of them, 1, 2, 3. And the way it goes is the more you have the drop, the better the indicator is. So if the drop doesn't go all the way down, it can usually be a sign of nonlinearity in your structure, which is typical of any structure, or other cases, maybe dry friction or something else. I will show you how to do the estimation with the polyfrac estimator. You choose one here and you hit next. Now, one important thing with these two boundaries, you adjust your let's say your lower and upper limits of your analysis. So we measured from 0 to 400. This is 400. And you want it to be maybe just a little shy of it, and maybe a little more of here. So you don't want to get all the zero frequencies transitions. Hit next. Now what the software is asking you is to identify how many dips you see. In our case, this is 3, but it's not a hard choice. So let's do 3. Let's go next. You can see this. Okay, we'll talk about this graph in a second, but you can also do, let's say, 5 and get slightly more time, but basically the same result. So what we see, let's do legend. So what we see here, this plot is called the stabilization diagram. Stabilizations come from the degree of polynomial that the software is trying to fit to your data. In our case, because we identified 5 dips, the software is trying to identify to fit 9-degree polynomial up until 31st degree into your data. And these dots, they say each time your pole or your mathematically it's pole, in the real world it will be your natural frequency. Each time this pole stays put. In other words, in each time it is stable. And you really want to look for this stable identifiers. You have this small legend here. So, and what you are left to do here is to click on the ones that you liked. So, for example, we are choosing this one. We are choosing this, and we are also choosing this stable mode. Stable is the best outcome, but if you don't have it, let's say your structure is very prone to nonlinearity, a lot of dry friction, you might not be able to get very clean frequencies and natural modes. So you get what you have. So this diagram, let's see, let's go 3 again. This is a mathematical entity, so you can see that with 3 it gets to a stable mode faster. So let's choose 3 of them, and next plot will actually already show you the modes. This is exciting. We can see the labels. This is the root, and this is our structure. The manipulation of this window is the same as before. So Shift is zoom, and Control is moving. And if you do nothing, just with the mouse click, it rotates. So this is our first natural frequency. You have the stats here. So the frequency is 23.5. This is the modal damping. This rest of these values are your indicators of the quality of your feed. So ideally you want to aim to 0 degrees here and something that's close to 100%, all three of them. You can read more about it in the manual. So you can see that this is our twisting mode. Let's go to the next shape. Okay, so this one is slightly more involved. So I tend to say that this is the second bending of the vertical portion. Again, the stats are okay. We are way below. We are near 0. Let's do even higher. And this one, you see, it's a kind of first bending of the horizontal T. But as with any natural mode, there is no such thing as moving only a portion of the structure. The whole structure has to move. So it reacts a little bit here. We hit next. We see the summary here. And each time that your estimation is not that good, let's say you're over 10 degrees of MPD here, it will be shown in pink, and if your discrepancy is bigger, it will be shown in red. So my remark here is it is your choice which modes to accept. The software won't tell you discard this or that mode. It will help you to do the decision. But it's the final choice is yours, and the reporting is on you. So we're saving 3 of them. Hit save, and we finish. If we go to the Explorer here, we can see already our modes here summarized. And this is about it. So you did your first modal analysis.